Thank you guys all for coming to the critical line of defense, teleprotection in the modern grid. Some housekeeping items first. There's a button up there with a button from your right hand corner. You can input any questions and we'll go through those at the very end. There's also a file icon. You can see our white paper and also our brochure for um, our tornado product line. Next slide, please. So our presenters for today are Mark Fetchy, VP of Sales, and Bob Black, our Senior Support Engineer and Lead Trainer.
Oh, all right. I think it goes to me next, right?
Yeah.
All right. Hi, everyone. I'm going to try to remember to look at the correct camera. I'm so used to being on webinars and Zoom calls where I'm having to look at the camera on my laptop, but there's one up in front of me, so I'll try to focus on that. My name is Mark Fetchy. I'm the Vice President of Sales, U.S. Sales for Ubiik. And I just want to start off by giving a little bit of background on who Ubiik is, and might be a company that you haven't heard of. But Ubiik was founded in 2016, really focused on AMI type solutions in the eastern part of the globe. Compact LTE, private LTE base stations, and a waitlist protocol for doing AMI. Mimomax was focused more on narrowband technologies, point-to-point, point-to-multipoint, in several different bands across the globe. And these two companies came together in 2023 to provide a broad range of wireless portfolios all the way from narrowband to broadband. In the US, we operate both under the name of Ubiik and Ubiik Mimomax. So you might have heard of both of those names, but full range of wireless solutions for critical infrastructures like electric utilities, what we'll be talking about today, but also for other companies such as public safety agencies. And you'll see some other critical infrastructure mining type companies on this limited customer list here. But a lot of electric utility companies, that's kind of where both Ubiik and Mimomax got their start, was in that utility space. So today we're going to talk a little bit about teleprotection, about why grid physics is kind of changing the need for faster response times in the communications world. So as Jenny mentioned, there's a white paper. If you have a chance to download that, it's going to take some time. It's a very extensive white paper written by our own Marco Pengas, who did a very extensive deep dive into some of these new issues that are popping up when it relates to teleprotection and grid coordination. And one of the main things in that white paper that you'll see, and kind of the base for what we're talking about today, is a system collapse that occurred about a year ago in the Iberian Peninsula. So Spain and Portugal had a massive power outage that was a cascade event that occurred in April of 2025. And in that event, what you'll see in the white paper is that a series of events happened that caused this massive blackout. It started with the operators seeing some instability in the grid and dealing with things manually. And then some things happened where some massive load shedding happened, generation tripping off of line. And in a very short period of time, it went from an event that operators were able to handle manually to a very short window of about 8 seconds where a number of events happened that caused a massive amount of frequency instability. You see up there on there that the frequency went from to 48 hertz in the span of 3 seconds. Now, just for level set everyone, Europe uses a 50 hertz frequency as opposed to here in North America, we use 60 hertz. So a big shift of 2 hertz, still pretty big, not a massive 12 hertz shift like it would have been here in the States. But that study in the Iberian Peninsula shows that there is really zero tolerance that utilities find themselves in when doing these massive coordinations over very large areas. Contrast that with an event that took place in the Italian Peninsula in 2003. 2003, Italy, the event, cascading event, occurred over about 27 minutes. So time for operators to manually interact, manually do some intervention, and kind of manage that outage. It still ended up being a large outage, but it was able to be handled manually. But now, when we're talking about events that occur in short time span, 8 seconds, 3 seconds, there really isn't time for the human brain to even react to question what's going on. Kind of reminds me of that movie that talking about the miracle on the Hudson, where the pilots had to show that they had to take time to ingest the material before they could understand what was going on and react. Same type of thing. The human brain takes some time to react, and that's why we need critical communication solutions that can react quickly. So there's less time for latency in our communication systems because of the need for fast response times. So why is this changing? Well, really, it's changing because of the characteristics of the modern grid. Back in 2003, when the Italian Peninsula outage happened, it was really traditional generation, large generation plants, lots of rotational inertia that could kind of counteract frequency changes. Contrast that with today in 2025, uh, where there is a lot of distributed energy resources, wind, solar, and inverter-based generation that isn't able to withstand those fluctuations in the grid. Also, the wide area interconnections and coupling of those distributed resources together, and the need to coordinate between all these distributed resources as opposed to a few generation plants over a large area. When I was coming over here, or I'm in our Phoenix office, I was flying over from Houston, flying over West Texas, and I looked down, flying over the Permian Basin area, and I obviously saw lots of pump jacks pumping oil and everything, but also lots of wind, and I could even see some solar farms. So I pulled up ERCOT's website. ERCOT is the Electric Reliability Council of Texas that runs the electric grid. And at that particular time, 78% of the state of Texas was powered by wind and solar. Very little traditional generation, very little nuclear, very little natural gas spinning generation was actually powering the grid at the time. So we're seeing that everywhere, and I'm sure you're seeing it in your utilities and the places you live. Lots more of wind, solar, and other inverter-based technologies. And so what that leads to is the need for a very low latency, deterministic communication system that can allow those communication messages to propagate over this large, wide area interconnected system. And what you'll see in the white paper is if we take it down to the least common denominator, that 3-second amount of time where that frequency instability happened, and say that's our bounding factor. If we have to respond within 3 seconds, the grid needs to respond within 3 seconds. And on average, a large system needs about 300 coordination messages to be sent across it in that 3-second time period. That makes our window for communications down to about 10 milliseconds. So you'll see that in the white paper where we talk about this 10 millisecond critical time that is needed. Like I said, it's a long white paper, but I've learned more reading that white paper than in the 30 years that I've spent in communication business supporting electric utilities. So that's kind of the basis for what we're talking about today. To delve in that a little bit more, I'm going to turn it over to Bob Black here, and he's going to talk a little bit about teleprotection.
Thank you, Mark. Yeah, today basically I'm just going to give you a high-end superficial view of the teleprotection and the key terms and that's used in teleprotection and then give you a little bit of focus into the narrowband solution that we provide and how it works and the type of the very characteristic details as such. You can get a lot more detail, of course, with this, also with the net white paper that we provide. So feel free to actually look through that as well. And that, so given here, we're just showing you an example as far as the teleprotection, and that in our narrowband solution right here is collected, where basically that communications links between the two relay switches right here that are exampled. And that's where we will give two key terms. The first one we want to talk about is asymmetry. These are the two terms that basically any communications grid are for teleprotection needs to be aware of, as far as in order to actually coordinate that time determination values to determine whether or not it's going to trip or not trip in that. So in the case of asymmetry, we're looking at the difference in the delay time it takes to get from basically one side from one relay over to the other relay to send that messages as far as depending on the actual schema that's used. And that's why we're talking about, in the grand scheme of things, we need basically to get within 10 milliseconds. We need that link to be within 10 milliseconds to be accurate and to do that termination in order to determine as far as the successfully grid failover or not be able to meet that grid failover requirement in that. So with that, we also have to take in account jitter, which is basically that delay that happens between the packet arrivals at different times. So for example, is illustrated here is you have a packet is sent on the communication lines, is received at A at a certain given speed. Another packet is then sent, and the difference between those two packets arriving, and that is what basically makes our difference of what we call our jitter in that. So basically, any teleprotection scheme needs to account for that latency asymmetry values and those jitter values in order to basically remain in sync to determine what's going to go on. In the teleprotection scheme, we talk about basically on the lines, which is zone 1 and zone 2. So zone 1 is essentially that zone that covers typically 80 to 90% of that main line areas for basically that communication between the one relay switch and the other relay switch on the main line. Then when we talk about zone 2, that covers the remaining switch, which could be offshoot branches, etc. in that. In that zone 2, that's where we get into the maximum of 300 milliseconds before time needs to react. A determination needs to be made in that for that failover protection to occur in that. So when you see zone 1 and zone 2 and that's what we were talking about in the teleprotection schemes. They're talking about the main line, and then they're talking about offshoot zone lines, adjacent lines and such that come off of the main line that covers into zone 2. You might see also references to zone 3 and zone 4s, and that which is redundancy and other type of systems that come off of the lines. They're also that we covered in the teleprotection schemas. Okay, so what types of tripping schemas are there out there in that? There's different types. We have the direct transfer trip, which is basically that's from going from the left to the right on this slide. You're looking at going from the more security, where it's if you have an instant failover reaction in the relay switch, to a more dependable. And what do we mean by that is basically a differential between you want it to fail over immediately on the trip, or you want a more dependable net where you avoid maybe false trips and more deterministic as far as on the grid and that, so you're providing the necessary support and preventing cascade events and stuff like that. So on the left side, we have a direct transfer trips immediately on the remote signal as such. Then you get into a direct comparison blocking, which basically in that type of schema, you have a signal that's sent, a blocking signal that's sent from the relays along the lines that basically indicates a trip condition for that. The problem with that type of schema is, although it's very quick and more secure, if you have lightning or other weather type of events, that could actually cause an actual indication as far as the trip of false and tripping that which you would want. And so then you go on into directional comparison blocking, and that's also a 2 frequency type of system where it sends a blocking signal, and then the other side will also receive that select, so they can basically compare across the link between the two. And in that case, that's more, once again, that's more certain, but it also mitigates some of the accidental or false indicators that can cause a trip in that type of system. That brings us to more of the modern day systems out there, which is the PUT and the POT, where you have permissive undertaking transfer and you have permissive overreaching transfer options in that. Underreaching being in zone 1, overreaching that goes on extend over to zone 2, and that. Difference in that we'll talk about specifically is on this slide with the POT versus the PUT, and that whereas with permissive overreaching transfer tip, uses 2 frequencies. It's capable to operate by requiring both ends of the line to detect a fault in that. And so basically one side and they signal to each other to indicate there's a fault, so there's a delay as such to make that deterministic to whether or not to fail over in that. The difference between the POT and the PUT is PUT actually requires a response from the far end as such to indicate whether a true failover is necessary in that. So in that deterministic. So POT, you can actually have the fail on one side and that failover will occur, and that it doesn't require the other end, so you can lose the remote end and still have a failover transfer. Whereas in PUT, you actually have to have that deterministic between the two and that to actually have a failover occur. So PUT is required, gives you the most dependability on the grid and maintaining it, so you don't have false indications of false indicators, and that will basically fail you over. Whereas POT gives you the most more security versus it. So that's the difference between the two. The key things, as we mentioned up at the very front, all of this is being as far as time based. Two things that can, in order for you to use PUT or POT, you got to have something within the system that measures time accurately in order to have that difference of the understanding of the asymmetry and the jitter time and that between those packets that are sent for communications across that. All of that is to reduce that time delay. If you have the time that it takes for the actual relay processing, you have the time for the breaker operation. So you want to minimize that time for the actual communications using a POT or PUT type of a system, which have to send that signal. You want to minimize that time that's on that actual medium. In this case, the target goal here is within 10 milliseconds. Preferably, if you can get down to 5 milliseconds, that's where you want to reach. So what type of solutions are for that medium? What carries that signal between the two in order to support a PUT or a POT type of teleprotection schema? And so we have in here, we have the narrowband solutions, which we'll focus about on the Ubiik solution that we have specifically designed to support teleprotection. Where there's talk about microwave and fiber and the different benefits with it. Fiber obviously provides the highest data throughput and efficiency rate on that because it's a hard line that goes across between the two sites, but has the limitations as far as obviously with cost and as far as infrastructure, as far as location. There's simply some sites between your sites that because of the geography or because of other infrastructure and such like that, it's not cost effective or even really physically possible to actually have fiber as an option. The same thing kind of the limitations of microwave. Yeah, you can get over the air, but you need that line of sight options as far as support for a microwave link that in some cases, based on where you want that relay switch to at, where the communication needs to be, then you're going to be focused on a narrowband is a solution. And in many cases, in that many utilities will actually use one or more of these type of options within it. So one is a primary, and then one is as a redundant as well. So you may see utilities using more than one type of solution for a particular teleprotection link. So in our scheme of things, we're going to introduce basically my narrowband solution for teleprotection in the Tornado line of products. And that we essentially have two radios that present, which is one is our standard Tornado radio product line, which supports teleprotection, and then our high-powered radio that also supports teleprotection schema in that. For any of the schemas that we presented, and that the difference between the two is one is a operate at a quarter watt. So it offers that flexibility for basically sites and that run on solar, et cetera, and that you can have that link, but you're not demanding a lot of critical power cycle for location and that. And then for those links that you need that distance between the two and all that, and great throughput for the lowest latency options in that, then you have the Tornado X, which is our 2.5 watt radio link that provides that for a narrowband solution. Key in here and that. So this is the difference that kind of shows. That's what we're showing our link with this with the two radios providing that narrowband solution. Where the relays where basically you have the master and the slave radio and a point-to-point solution that provides that. And this, how do they work and what makes them maybe different from other narrowband solutions is MIMO link and that. So if you're not familiar with MIMO technology within radios and that, it's very similar to what your routers in your home might use for Wi-Fi and that. They help basically overcome other communications in the air for interference, and they provide that diversity in the signal to also break down your signal for reliability on receiving a signal and breaking it out. in this case, basically our signal, we're transmitting both on the horizontal and the vertical, that same packets, 2 transmitters. You get that reliability then when those packets receive the other side, that the radio can then break it out and deliver the packet reliability. This is also what allows MIMO technology, allows the tornado to have the capacity that's twice to 4 times greater than what you might get in a traditional legacy SISO type radio. And that for teleprotection, it's specifically what gets us into those latencies less than 5 milliseconds. All right. With that protection, and that not only does the Tornado line of products give you that option as a teleprotection link medium to carry those signals, we also have redundancy with the radio itself. So if something mechanically happens with the radio, or even in some cases, when customers want to exercise another line path, and that when we provide a 1+1 option, where basically you have 2 radios on site that provide that link. Those radios are synced in such a way that they can immediately take over the link. So if one radio goes down, the other radio picks it right back up to give you that redundancy, both on that side of things for the teleprotection of that. In addition, something that's unique that we offer with the Tornado line of products that you won't find in other radios, and that is the redundancy in SISO. So not only do we have that 1+1 option, if a customer doesn't want to use that option, but they still would like that redundancy, we have a SISO failover, where basically if one side of the radio does have a failure, or if there's link or something blocking within the path that affects that RF path and that, then the radio can actually revert to a SISO mode in order to maintain that link up to give you that kind of redundancy in the link, as well as it would be if it were MIMO technology. And then you can always restore that later on with that. So that's one of the things that's unique within the Tornado line of products that you won't find in other legacy type of radio products. We also, as I mentioned early on, that there could be sites where obviously fiber isn't an option because of the physical limitations, or personally for microwave limitations as well. You don't have a line of sight. You're talking about areas in mountain valleys and that you needed that teleprotection link to. Well, you can also be challenged by multipath and other RF factors that affect that signal going across in that typical traditional multipath for microwave and maybe even the MIMO products would have a challenge with. We actually have the ability with that link to actually do SISO to space diversity, where essentially you can actually space 2 antennas with the MIMO link Tornado radio and have an offset, and the radio will then be able to compensate because with that spatial diversity to give you a better, it compensates for that multipath. It compensates for other types of factors in the RF that you could possibly get within that path in order to give you a reliable link for teleprotection. Okay, it's all about latency and deterministic latency, and that so that the systems can make a decision, deterministic determination as far as actually doing the failover or not doing a failover, responding to a false flag event, or actually responding to an actual failure on the grid. What's your time difference in that? It can't exceed 95% of that time. So looking at the numbers, so this actually gives you the values in that over the type of interfaces we typically would do for teleprotection. This is the legacy G703 that's used by utilities, and then the more common fiber optic 3794 type connections that would go basically into the radio. The Tornado already has all of the basically features to fully integrate and communicate with these type of converters. So that basically the signals in that. In addition to that, not only do you have this already built into the radio for integrate, it also has that ability to monitor the actual link status for the physical connections to those converters and that. So you can actually remotely log into a radio and actually check on the status of your fiber connection, whether it's G703 or the 3794 type of connection to the radio, to determine if it's good or bad for monitoring purposes in that. These values you show here are the typical latency values that you would get one way across a teleprotection link. Notice the higher the modulation rate, the lower the actual latency is for the response in that, which might be a little bit different than what most people might think as far as lower latency might be in lower modulation rates. But in this case, because we can support up to 200 kilohertz on our MIMO radio, we can get latencies down to 0.08 milliseconds on the 256 QAM link. So not just the numbers on that, these are actual tests that we showed. They show a net probe using a net probe 2000 tester. This is the two-way latency ratio you can expect across a C3794 link, or even like an RS-232G703 type of link. So you see here, we achieve not just the 10 millisecond, but also achieve down to less than that 5 millisecond most desirable latency that we want to get for that comms part for teleprotection. All right, so what's this gives the resilience? This the other big thing about MIMO is that resiliencies. And that case example in New Zealand when they got hit by an earthquake, it was like 2003 time frame. They with MIMO link in that, because you're transmitting on the MIMO principles horizontal and vertical in that. As the radio and the poles lean over, etc., and the infrastructure changes, a microwave link can't support it. Once you no longer have that site on from microwave point A to point B, then you've pretty much lost your link. But a MIMO radio can compensate. You know, if this, as the poles, what happened in the New Zealand earthquake, as the poles leaned over and such because of the earthquake, the links were still maintained, because it was all that changed was basically a differentiation between the horizontal and the vertical. It may have degraded signal in one polarity, but because they still receive the same packets on the other polarity, the radio makes that differentiation. It's being able to maintain the link. Something unique for applications to consider for utilities out there, or whether they need to consider about flooding or earthquakes as such, but they need that link to still stay up that other technologies wouldn't be able to provide, such as fiber in an earthquake or microwave. Yeah. All right, so with the challenge in that, I'll bring over to Mark.
Yeah, so Bob, apparently you and I talked a lot faster than we did during practice, so we finished a lot sooner. But this is another case study that we have, that a very challenging environment, New Zealand case study, where they couldn't deploy fiber just because of the rugged terrain and everything. So we ended up deploying the MIMO link, what we call our optimized protection variant, which is our teleprotection version of the tornado radio, because it handled some non-line of sight paths. So in their case, the 5 milliseconds of latency and the 55 nanoseconds of jitter, we were able to meet that with some very challenging environments. So like I said, I know we finished a lot faster, and we may have some questions. Bob, why don't you go ahead and come back in here, because I'm sure there'll be some that I'm not able to answer. Just as we mentioned at the beginning, there are some documents there, the white paper, teleprotection brochure that gives some more details. And then Jenny, are you there?
Yeah, we have a few questions, but just a reminder that the right top hand corner, you can ask more questions. So one of the questions we got is, are we going to make the slides available?
Oh, yeah, absolutely. Yes, we'll anyone who registered, Jenny will package these slides up and make sure that everyone is able to get those slides. Jenny, will that come? Sorry, I keep on looking down at the speaker over there. Will that come via email, or do you know what? Is that just going to be like a follow-up email?
It'll be a follow-up email.
Okay, great. And then also, if in that follow-up email, if you're not able to get to your question right now, you can't think of something, and you want to respond to that when we send out the slides, please respond back with any other additional questions. We'll also type up all these Q&As. We'll send that out as well. Jenny, can we just attach that at the end after this slide, just like attach it in the same document?
Yes, for sure. And then Another question is, can you provide the link to white paper?
Okay. Yeah, we can provide a separate link if you can't, if you're not able to access it in the, it should be in the GoToMeeting
Should be in
under documents.
Yes.
But if you're not able to get that, we can also send out a link for that. Sure.
Yeah. It's the tab right next to the question button. If you hit there, you can download the white paper. Um, Another question is, from your chart, it seems like the modulation gets higher, latency gets lower. How do you pick which modulation and bandwidth to use?
Yeah,
Okay.
good question.
Yeah.
Let me get back to that slide real quick. If that's okay, Bob. I
Yeah.
assume they were talking about this one
Yeah, I know what
here.
it's talking about.
Would be my
Yeah,
guess.
as far as picking what's the best modulation rate or a given rate in that, one of the things that we do with any of the customers we've done with Teleprotection is we do an RF pass study. That's typically free service, and then of course we also even have paid services for that to give you the greatest detail on what you can expect across from the site from point A to point B. But within that, maybe you don't need the quantitative. We always tell you what you will maximum possibility, and we always plan for about at least 20 dB fade of margin. That way, you know you have a reliable RF link between A and B, and that. And if you most times you're not going to need all that throughput, especially if you're only carrying over the transfer, basically that relay. You don't need any management overhead or anything like that. Then typically you can get down to the lower modulation rates, which gives you more reliability in that because you get more fade margin, et cetera, in that. So you don't have to go with the highest, which gives you the fastest. But the way we usually support our customers is we typically do the study and let them know, hey, from point A to point B, this is what you can expect to operate that, and this is what we recommend as far as setting for modulation rate.
Okay.
That.
Now you brought up something there that we didn't even touch on. We talked about latency here, but the channel bandwidth and the modulation also relates to throughput. I know this wasn't necessarily the question, and maybe we should have included a chart with throughput. But can you speak generally? What obviously the wider the bandwidth, the higher the modulation, the more the throughput. But what can we get up to in a narrow band? Like how much throughput? If we went with the maximum, or how much?
Up to 200 kilohertz. Yeah, that's up to 5 meg.
So we can do 5 megahertz.
Yeah, almost microwave.
Okay, so 5 megabits per second throughput on a 200 kilohertz 256 QAM link.
Yeah.
Okay.
Yeah. Which means then obviously you have other avenues to support that. One of the other unique things I didn't mention is such the Tornado automatically prioritizes that teleprotection link traffic.
Okay.
So it automatically creates a tunnel within on the RF link itself that separates management type traffic. So if you want to carry other traffic, it won't mitigate or interfere with that delivery of that other packet. So if something were to happen, you had to step down in modulation, and that the radios will prioritize delivery of teleprotection packets over any other type of management traffic, whether it's monitoring for VNS and MP or remote logging into the radio, et cetera, like that type of traffic, or any other TCP/IP traffic.
Okay. So going back to the original question about how do you choose the latency, we're gonna do the study that says, hey, this is based on the path that's out there, the terrain and everything, this is the maximum modulation you can go with. But if you don't need all that throughput, for example, if you don't need 5 megabits, if you're just sending the transfer trip, which is obviously you could lower that. You could lower the QAM down to 16 and increase that fade margin, right? I think that's what you were saying. So go from 20 and go more, and allow for additional reliability, right?
Oh yeah, I mean it's a difference. That's one of the unique things. The radio can receive down to minus 115 in a QPSK link.
Oh, it goes
so almost right there at the noise floor in most locations in that, and still break out the signal. So QAM 16 in that you're minus 105. That's a very low signal to break out. It gives you that idea of what you can maintain.
Okay. All right. Hopefully we answered that question. Jenny, what's next?
Okay, we got quite a few questions. What's the most reliable modulation rate for teleprotection?
Probably most of our customers, it sits around 16 QAM.
Okay.
Yeah, for what that
So
carries.
that's that good balance between fade margin and throughput and latency and everything.
For what their needs are. Yep.
And sorry, I shouldn't have gone off this slide. So 16 QAM. So even in in some of these, even in the very narrow band channels, we're still talking theoretically of almost that 10 millisecond range. But bump it up to a 25, and you definitely get below that 10 milliseconds, even with definitely with 16 QAM. And, okay. So 16 QAM is kind of the sweet spot.
It's kind of the sweet spot.
Okay.
Yeah.
All right.
Okay. Don't most utilities do this with fiber?
Yeah. Well, and Bob, you kind of touched on this. Yeah. I mean, that's the I guess best way, right? That you have a direct fiber between your 2 points, but that also comes with some cost and complexity. I mean, obviously, you're building a new line, put the fiber in, and you can do it with fiber. But also, we know that fiber it does break sometimes, even on transmission lines. Actually, so I live in the northwest side of Houston, and we actually had actually it was about April, about the same time as the Iberian thing. We had no, it was the year before. We had a tornado come through our area and actually dropped the transmission line. So I think you mentioned when you were talking that MIMO link could be a good back, even if you have fiber. MIMO link would be a good backup, a level of redundancy, and a relatively inexpensive level of redundancy. But yeah, a lot of utilities do it with fiber, but if fiber it takes time to install and it's expensive. So if you need something up and running quickly, or if you need a lower cost solution, or even a backup, MIMO link could definitely do it. But yeah, fiber is a lot of utilities use fiber, and there's a lot of fiber going in and continuing to go in.
Sounds good. Sorry, there's a lot of questions coming in, so please hold tight if your question is not being answered. Another one. How do you keep jitter controlled on your radios?
One of the things on the tornadoes that we've constantly, and that can't even be turned off, is we implement forward error correction. It goes through the buffer, and then it's recalculated on both sides. Remember, I mentioned one of the things about the MIMO principal radio is that same packet is transmitted on both sides of the radio for both the horizontal and the vertical polarity. And so we compare those of that time, and that differentiation is how we basically control and compensate for jitter, so that we have basically control that jitter rate that's going across the RF side of the radio link. As using MIMO principles that it would be a lot more difficult and latency delay in a SISO type radio product.
Okay, and latency delay that equates to jitter.
To jitter.
Okay, I think you were saying it because jitter, if I remember correctly, trying to put
is the time difference.
Is the time difference? So
between the packets.
So latency changes over a period of time. That's what you're talking about, the need for deterministic latency, right? So
so you need to be able to control that because you want consistency in your jitter rate. And that's how we implement it basically in that calculations that are done across both polarities. Radios, both sides of the radio basically share that information to make those calculations and compensate for jitter.
All right. So that answered that one.
Sounds good. What's the typical availability your teleprotection customers are looking for?
Availability.
It's 5 nines. Yeah, 5 nines availability in that. And when we do these PAP studies and that, we do those calculations as such to kind of let the customer know what are your this. So that's one of the reasons why when we do a study, we let the customer know we're targeting 5 nines. So that's why we let them know what the optimum modulation rate or bandwidth is for that between the two sites for that point-to-point link.
Okay. Yeah, and if I remember from my early days as being an engineer, one of the first things I was doing was microwave path studies and the understanding the relationship between fade margin and reliability, right? If I remember correctly, you could get a path that's 4 nines reliable with a lower fade margin, but if you want a good fade margin, one kind of dictates the other, right? If you want 5 nines reliability, it says you have to have this much fade margin to account for that, right?
And that's a lot of times that's why when we, especially teleprotection, we do those path studies and that we go higher in build in 20 dB of fade margin versus maybe the standard 10 and 15 dB that I've seen others do, because we need to achieve the 5.9s. We understand the teleprotection.
So even with our 5.9s calculations, it sounds like we're putting a little bit extra.
We're doing
a little bit extra margin to make sure that because it's teleprotection is so critical, right? That you have to get that message through.
And you got to recognize the difference between what you do on the computer simulation, versus real life when you actually put a link up.
Yeah. Okay. So 5.9s is the goal, but you need to verify that in the field. Okay. All right.
The slide shows a bunch of different serial interfaces. How do you choose which one to use?
The 703, the fiber, this. So if you've seen the radios, you saw the picture on that, you notice there are 2 serial ports on the radio. Typically, that allows our customers, you can use both serial ports and simultaneously, there's not a conflict in there. They're easily transferred and carried over to the RF side of the radio. You can use one serial port for one communication means, and you can use the other serial port for the other communication needs. Typically, our customers will use serial port 1 for the actual converter, G703 or RS-230 conversion, or the fiber optic converter, the C3794, then that connects to the radio, and that. So that's typically, and I said GUI interface for setup. It's fairly straightforward for the customer, and that's why I said I'll also use the GUI's nice, because it also give you some indicators of the connections of those converters. So you can actually log in, as I mentioned, you can log into the radio and actually check the actual status of your connection on that side of the things. Using the radio basically is a way to monitor your actual physical side connection of the teleprotection link.
So the radio itself does. So if you're using which is the fiber one's 3794.
C3794.
If you're using 3794, the fiber one, we don't have a direct fiber connection on the Tornado radio. We have to use this converter. But the radio knows it's there, and so you're monitoring that.
Yeah. It will tell you it's receiving packets. You can see packet counts. You can monitor for that.
Okay. What frequency bands do these radios operate? Which band gives you 5 megabits per second?
Did we not? I guess we didn't cover that.
And the bands, I guess we don't have an actual slide. We actually provide 700 upper A block radios. Is one example of that we provide in that spectrum. 900, 806 to 960, depending on the country as far as what frequency. So the radio supports from anywhere from 806 to 960 on the 900 band radios. And then we do have UHF radios. We do have 400.
But those aren't the 200. We don't do 200 kilohertz.
Yeah, we don't do 200 kilohertz on those radios.
You're not going to get a 200
those would
kilohertz.
Be standard. Yeah, those would be our standard radio products in that mechanism. But we do have that in that range for the Tornado products.
Okay. Because I think, Jenny, the question was around the 200 kilohertz to get the 5 megabits.
Yes.
Yeah. Okay.
So in which case that's our 900 and our 700.
900 and 700.
I can do that.
Okay. How does going sizel affect latency?
Good question. Obviously you have a differentiation.
You know what? We forgot to mention it. We also have James Dowell on the phone. Yeah. James, maybe this one might sound like you're sorry.
Yeah.
Sound like you're struggling.
No.
So I might want to turn it over to James.
James could. Yeah.
James is our tornado guru out of Christchurch, New Zealand. James, are you on the line?
Yeah, I'm here, Matt.
Can you answer that one about how SISO affects latency?
Yeah. So the propagation of the radio signal for SISO and MIMO is unaffected, but the throughput is half with SISO compared to MIMO. And the error correction blocks then take twice as long. So, and most of the latency is from the error correction. So it is approximately doubled. with the MIMO radio with CISO fallback, which is another option. So as far as CISO, we've got the full MIMO radio that's running MIMO all the time, or we've got a MIMO radio with CISO fallback. So that means if for some reason the RF channel is not performing well with MIMO, that it can fall back to CISO. So that might be if there was damage to, for example, the antenna or feeder system, and you only had one working polarization on the antenna. And then we have the CISO with space diversity, which uses the same, they all use the same radio hardware. So the CISO with space diversity has two antennas, and in that install case, you mount them with the same polarization, but with some separation. The MIMO only operation has the lowest latency, and then either MIMO with CISO fallback or CISO diversity they actually add latency in the MIMO mode so that when it falls back to CISO, that the latency is constant, because a change in latency is not something that teleprotection handles easily.
Right.
So we can provide a more complete table of latency that has the CISO and MIMO difference as well, but it is in the order of, it's a little bit less than double the MIMO latency.
Thank you so much. Next question is, what's the maximum distance the radio links can reach with minimum modulation rate?
Ooh. Wow.
That's a good question.
Is that another James question? Or can you get that one?
I've tested in the field in that example customer I've gotten QPSK at 36 miles, and that's a standard radio. So that's a quarter watt radio. And I talked about very low RSSI receive right at the noise floor and still break out the signal and that. So that's a QPSK link. That was about 36 miles. That was in Oregon. But we've had some links that are even longer than that. James, you remember the one link? I think it was the Greek islands or somewhere out there that was.
Yeah, in Samoa and the Pacific Islands, we've had a 120-kilometer link. Actually running 256 QAM.
Whoa! There you
go. The point-to-point radio system, the protocol for the radios doesn't really have a limitation on distance. The antenna heights at both ends of the link have a big impact. So the 36 mile pass Bob talked about.
The Purnell zones for that are actually in trees.
Antenna heights. In Washington State overland, we've also had a 60-mile path with 256 QAM between two hilltops.
Okay, so I think what you said is there's nothing in the protocol. It's all just the physics, right? The physics of power, free space loss and obstructions and Fresnel zone clearance and all those other things that I'm remembering from back when I was doing path studies. It's what it sounds like.
Yeah. So if you can get the signal level to the far end, then that whatever modulation that signal level supports with your fade margin for reliability, be what you can get pathwise, and it can be 60 miles or more when you've got high sites.
Okay.
Sounds good. Another question is what's the installation process for the tornado radio and for a teleprotection link?
The installation
Installation.
process.
Yeah,
Oh,
how
how do
easy
you
is it?
install it? We offer whether it's depending on whether it's the standard radio or the high powered radio. With the standard radio, you actually have a lot of different options. It's not a very large radio. You can actually mount it. You can dim rail mount it. It's 19-inch rack mountable as far as inside of an enclosure, it has a lot of tolerances in regards to both be operating in a hot environment or even a very severe cold environment. Because we've deployed in Minnesota, we deployed in the cold and -0 temperatures, and in the heat of the summer here in Arizona, where we're hosting at. So it offers a lot of flexibility. The high-powered variant, that 2.5 watt, it is a 19-inch rack mount radio. That's typically in where you would provide an enclosure. Most teleprotection, that's typically where you would mount ends for those customers that would want to utilize that option anyway. A huge another flexibility is power. How do you power the radio? And flexibility as far as powering the radio. Both radios support from 12 VDC to 60 VDC, and so that gives you a lot of options as far as power, what power you need to lead into the radio for site planning.
Yeah, that's good. I know, but back from my time at Motorola, we had some that were 12 volts DC and some stuff that was 48 volts DC. So having that wide range gives the ability to not have to have any of those DC to DC converters if your plant is already 12 volts or already 48. Okay, that's good. What else, Jenny? We've got a few more minutes left. Oh, did we lose Jenny? Jenny, you still there?
I apologize, I was muted. Sorry, we're coming towards the end of the webinar. If we didn't answer any questions, feel free to message us. We'll email you the answers. Another one is, does the tornado offer alarms or alarming or monitoring options?
Oh yeah, for sure. And as mentioned about segregating, prioritize the teleprotection packet set, but you still have the ability to carry management traffic, and includes SNMP, DNP3 type monitoring, alarms and alerts, and that, so that if you have a knock system or a knock net where you're monitoring the active grid and stuff like that, the radio can send you alert messages to indicate an RF downage or another condition state or something on the connection to the serial or whatever, that will let you know that there's a problem on site. It's easily integratable because we're supporting SNMP or DNP3 into a network management system for that monitoring purposes. And that we even have a few customers that we have on our GPIO port on the radio to actually output a RF sync state. So even if you don't have direct connect IP type monitoring system in a SCADA system or like that, we can alert the SCADA master by sending a signal via the GPIO port to indicate an RF link condition outage, alerting the network.
Okay. Jenny, let me jump in here. I don't know.
Yes.
I don't know if anyone asked the question or not, but being on the sales side, if this is a solution that sounds interesting to any of you, we do make short-term demos available. So if you want to set up a couple of our tornado radios in a lab environment, or I guess potentially even outdoors, but they're typically short-term loaners that we can give you. We can loan you a pair of radios. Bob will get them set up. He can walk you through how to test this. So if you really are skeptical about some of these latency results that you see up there, we're absolutely willing to give you a short-term loaner, let you play with it for a little while. See the proof's in the pudding.
That includes the cabling and attenuators and power supplies too. So it's a whole lab setup.
Okay. That we can let you borrow for a little while.
Okay, sounds good. Last question before we end. We're considering between microwave and narrowband for our teleprotection. Why should we choose your links over microwave?
Yeah, I'll take it not from necessarily the technical side. One thing that occurs to me is just ease of installation. microwave radios. Well, cost. Microwave radio is probably going to cost more than a narrowband radio. Installation is going to be easier. You don't have to deal with big microwave dishes. That's not necessarily. Typically, it's a Yagi antenna, much easier to install, not as much wind loading. And then, yeah, just so I guess cost of the radio, ease and ease of installation would be the two that I could think of. Why? Oh, and non-line of sight paths, right?
Yeah, non-line of sight
You mentioned
is
those,
a big one in that with the panel. Yeah, you don't need the aim like you do on a microwave
Right.
system for sure. So,
yeah, so I think those three things.
Okay, well, thank you guys so much. It is 2:58 Eastern Time. We will answer any other questions through email. As usual, if you want to keep in touch, email any one of us. It's just our first, last name at ubiik.com. And thank you again to our panelists, Mark, Bob, and also James.
Yeah, James, thanks for jumping in.
Thank you.
Thanks, everyone. Have a great day.